Hey guys, Touch Survives here, Tan Chen Hao here, and today in this video, we aim to derive the heat capacity of monoatomic and diatomic gases. In so doing, we'll understand the origin of the idea of degrees of freedom, as well as learn some interesting lessons from quantum mechanics and statistical mechanics. Namely, there's an interesting phenomenon I'd like to emphasize later that occurs at high temperatures, which we'll explore later. We'll begin the discussion by first talking about partition function. So, first of all, to describe gases, the study of gases in physics falls under the realm of statistical mechanics. Statistical mechanics is a statistical approach to physics. So, in statistical mechanics, the gases are what we call a canonical ensemble. They fall under this class of ensembles called the canonical ensembles, and is described by a partition function given by this formula. So, given a system with microstates, a list of microstates, we'll talk about what microstates is soon. The partition function is given by the sum over all the microstates of this factor over here, where beta is the inverse temperature and EI is the energy associated with each microstate. So what is a microstate? So a microstate is basically enough information to describe every single particle in the system. So for instance, if I say that I have a box of gas and I know the position and momentum of every single gas particle, then that will be a microstate. Of course, to describe a microstate, you need to specify a lot of information, that on the order of 10 to the power of 23 perhaps. But to do this sum over all the possible microstates seems like a very non-trivial task. However, you'll soon realize that this sum over all the possible microstates is actually just an integral over phase space. So yeah, so that is the concept of partition function. Okay, so it is standard procedure in statistical mechanics to write down the partition function, because many useful quantities can be derived from the partition function. Listed are a few below. So for instance, average energy is given by the derivative of log z, log the partition function with respect to inverse temperature, and here are the equations for the other quantities like entropy, Helmholtz free energy, and pressure. So basically, I just want to mention that the partition function is to statistical mechanics what like the equations of motion is to classical mechanics. If you want to solve a classical system, you write down the equations of motion, perhaps as a Lagrangian. If you want to solve a quantum system, you write down the Hamiltonian. You diagonalize the Hamiltonian operator. But in statistical mechanics, you want to solve a statistical system, then you write down the partition function, essentially. Yeah, so we'll focus on the average energy in this video, and we also calculate the heat capacity, which is just the derivative of average energy. Okay, so let us move on to an example, which is the monoatomic gas. So the energy of a single gas atom, we consider a single gas atom first, okay, and it's given by energy equals to P squared over 2m. That's the kinetic energy. We assume that the single gas atom is not under the influence of some potential. So the single gas atom is described by 6 numbers, 3 scalars for the momentum, and 3 scalars for the position. So the phase space is 6-dimensional, and the phase and the microstates, the list of all microstates is basically the list of all possible 6 real numbers there are. Okay, so when we want to do a sum over all the microstates, we are basically integrating from minus infinity to positive infinity of the positions and the momentum. So when you want to do the integral over phase space, you also need to include this factor 1 over h cubed, which is to make it dimensionally consistent, and it also plays some other role which we will not evaluate in this video. So as seen previously, when you want to do, when you calculate the partition function, you're summing over all the possible microstates I of e to the power of minus inverse temperature energy of the microstate. So in this case, we are integrating, which is just a sum, over all of phase space of this exponential of minus inverse temperature times the energy. So you can plug this formula into, plug the formula for the Hamiltonian into the partition function, and we'll get Gaussian integrals. You see it's a Gaussian in p squared. So you do the following Gaussian integral. There's 3 Gaussian integrals actually, and you get the following expression for the partition function. So you can realize that the partition function currently depends on temperature, or you can think of it as inverse temperature as well. So let's move on to n particles. So for n particles, the partition function is simply z1 to the power of n, because when you have n particles, then the energies of each particle adds, since there's no interaction potential. So the energies simply add, and since the energies add, then the exponent of the energy, the exponential of the energy would then multiply, and then the integral would just multiply or like factor out. So what I'm trying to say is that the partition function for n particles, n gas particles, n single gas atom, n monoatomic gas atoms is simply the product of n single atom partition functions. And there's also this factor of 1 over n factorial, because of the postulate that particles are indistinguishable in quantum mechanics. Of course, this is there. Of course, later when we calculate the average energy, it turns out this factor will be redundant because we are taking the logarithm and differentiating it. So this factor will disappear. However, even though this factor is irrelevant for the calculation of average energy, it is relevant for other quantities, like I think entropy. Yeah, so that's important to note. But in this case, this factor of 1 over n factorial is not too crucial for the discussion of this video. So we have the partition function for n particles. Now we want to obtain the average energy, so we just take the logarithm of it, and then we differentiate it with respect to the inverse temperature. So what we realize is that plugging in the expression here into here, we get these terms. So most of them are constants with respect to beta, except for this guy. So ln of beta differentiated, you get 1 over beta, and that is just kBT. So this is the formula for average energy, and we realize that it agrees with what we learned in a standard thermodynamics course. And we can calculate the heat capacity easily, and this concludes our derivation for the monoatomic gas. So that is the monoatomic gas, with a small caveat. Later I'll talk about it. So notice this factor of 3 over 2. This factor of 3 over 2 is because we have 3 Gaussian integrals from the momentum contribution to the Hamiltonian. So 3 over 2 is because we have 3 Gaussian integrals. We'll see more contributions later on. So let's move on to diatomic gas. So for the diatomic gas, we need to consider other terms in the Hamiltonian. So there's firstly the translational one, which is just p squared over 2m also, same as the monoatomic gas. Then there's also rotation, and there's also vibration. So because the energies add, the partition functions multiply. So the translation component remains the same, so we shall not we can refer back to the monoatomic gas for its calculation. However, let us investigate rotation and vibration. So for rotation, we first need to find the phase space for rotation. What is the phase space? So to find the phase space, we use Lagrangian mechanics, and we calculate the Lagrangian first. This is a Lagrangian for rotation, This is just the kinetic energy in polar coordinates. Then the conjugate momentum is given by the partial derivatives with respect to these derivatives. So we get the following conjugate momentum, and this means that for phase space we have p theta, p phi, theta, and phi. So we can calculate the Hamiltonian with the following formula, and that gives us this. Realize that this is just the rotational kinetic energy. And we then plonk this Hamiltonian into the partition function, which would give rise to two additional Gaussian integrals. So let's see, we have the integral over the phase space as mentioned here. We have found the phase space with the Lagrangian and by calculating the conjugate momenta, and then we do the exponential of the energy. So substituting this into here, we realize that there's a Gaussian integral here because you have p theta squared and then you integrate over p theta, and then you also have a Gaussian integral here because you have p phi squared and then you integrate over p phi. Then these are just angles that integrate from 0 to pi and 0 to 2 pi. So we realize we get this using the Gaussian formula up here again, using this formula. So we get the two Gaussian integrals, and we need to do this integral as well with respect to theta. So doing it, we simply get this. So now that we have this, we realize that it's 1 over beta, right? It's 1 over beta, which means that if we take the logarithm, it gives rise to a kBt term. So that's the energy of the rotation, and this is for a single diatomic molecule. If you want n diatomic molecules, then the total rotational energy will just be n times kb times t. Now for vibration, we repeat a similar procedure, except that now we have a kinetic term and this is a potential term, because vibrations is essentially a spring mass system. You have two balls and then they're connected with a spring. So for the vibration, you integrate over position, or rather displacement between the two balls, and momentum as well. And you get two Gaussian integrals once again, this one and this one. So you get two Gaussian integrals and we get this result. So you realize that it is also 1 over inverse temperature, and so taking the derivative, we get the energy of the vibration. The energy of the vibrational mode is kBt. So now putting it all together, we sum up all the energies, and we get that the energy, each molecule has average energy 7 over 2. Wait, but this doesn't sound very correct, right? Because in a standard thermodynamics course, we are told that the energy is 5 over 2, not 7 over 2. So isn't this the wrong answer? Well, we will learn that vibrational modes we typically learn that vibrational modes are not included, and therefore this is the answer. However, why is vibrational modes so-called not included? Well, it turns out that vibrational modes are included. However, vibrational modes only appear at high temperatures. So let us refer for the following graph over here. This graph is obtained experimentally. This graph is taken from this set of notes, which is taken from some chemistry textbook, I believe. So this graph is experimentally obtained, and we observe a non-constant relationship between heat capacity on the y-axis and temperature on the x-axis. So we see that around room temperature, which is around 300 Kelvin, we get 5 over 2, which is what we learn in a thermodynamics course usually. However, at higher temperatures, you see that becomes 7 over 2, and interestingly, at very low temperatures, becomes 3 over 2. So what is going on over here? In our calculation, we didn't see that there's a dependence of energy on we didn't see that there's a dependence of heat capacity on temperature did we? I mean, in our calculation, there wasn't any transition temperature of sorts. Well, that's because, surprise, it turns out that this phenomenon is due to quantum mechanics. And yeah, so let us see why. So when considering rotational modes in quantum mechanics, this is no longer the Hamiltonian. This is the Hamiltonian in the classical mechanics. However, in quantum mechanics, the Hamiltonian for rotation is this. Rather, this is the possible energy eigenstates or energy eigenvalues. And yeah, so there's also a degeneracy of 2j plus 1 for each j. So the rotational partition function becomes this. So the microstates are now discretized instead of having an integral over phase space. Now you have a sum over discrete energy levels or discrete microstates, and that is due to the quantization in quantum mechanics. So if you want to understand more of this equation, see angular momentum in quantum mechanics. And I also made a video on spin in quantum mechanics, which is slightly, you see similar formulas. Yeah, so that is why the partition function in quantum mechanics is different from the classical partition function. So how do we do this sum over here? Well, first thing, we actually don't evaluate the sum. We don't need to evaluate the sum to see why the phenomenon happens. So one thing we notice is that the negative exponential here, it should die off quickly if j gets too big, right? Provided that this term in the exponential is greater than 1. So if this term in the exponential is greater than 1, then j, as it gets higher, the exponential should kill off the terms really quickly such that they tend to 0. So if this is true, in this limit, which is basically at a low enough temperature, the higher j's vanish. And when the higher j's vanish, we are just left with the j equals to 0 mode, which corresponds to the partition function approximately equal to 1. And since it's constant, taking the logarithm and differentiating would just give us energy of rotation is 0. So what this basically says is that at low enough temperatures, the partition function, the quantum mechanical partition function given by this, is approximated as 1, and so the energy for the rotational modes is 0. In contrary, at higher temperatures, in this higher temperatures limit, in the limit of high temperatures, the sum can be approximated as an integral because each successive jump in j does not cause a huge jump in the total term in the exponent. So it can be approximated as an integral, and you realize that this is a very nice integral, and you get this. And this reproduces the result we got previously for the partition function, for the rotational partition function. So yeah, so in essence, why do rotational modes get frozen at lower temperatures? Yeah, why do the rotational modes get frozen at lower temperatures is because your microstates have now been quantized because you need to account for quantum mechanics, and as a result your partition function is affected. And so at low temperatures, your partition function is approximately equal to 1, and so there's no contribution to the average energy. Now however, at higher temperatures, it reproduces the classical results. So the freezing of the rotational modes is due to quantum mechanics, and that's why we observe that at low temperatures, the 5/2 becomes 3/2, and then once you go to high enough temperature, it goes back to 5/2 because you are in the regime where this integral applies. Okay, now for vibration. When considering vibrational modes, the quantum eigenenergies, basically the Hamiltonian, is given by this. So okay, this should be h over here. Let's just write it as h. So when you take the sum, you do the partition function calculation, you do this sum. This sum is basically a geometric progression and can be written as this or this. So we will notice two things. At low temperatures, in this limit, then in this limit, the denominator here vanishes, and we get that the partition function is approximately equals to just the numerator. And so we evaluate the partial derivatives and we get that energy is h bar omega over 2. Yeah, and then taking and this is just a constant addition to the energy, to the average energy. So if we take the derivative, then the heat capacity would not change. The heat capacity would, the derivative of E with respect to temperature is 0. So this might also be known as the 0-point energy of the harmonic oscillator. However, when you take the high temperature limit, then the vibrational modes, when we take the high temperature limit, then this is approximately equals to, the sinh of this is approximately equals to this thing itself, and that will mean that the vibrational partition function is just 1 over inverse temperature, and so you get that the average energy is kBT, and that reproduces the classical result, and hence at high temperatures we essentially unlock the vibrational modes. So in summary, we have derived the energy of a diatomic molecule, and we saw that there are 3 contributions. Number 1, translation, which occurs at all temperatures because there are no discretization as a result of quantum mechanics. Then there's rotational, which at 2 different regimes of temperatures gives different results. So at low temperatures, the rotational modes do not contribute to the average energy, whereas at high temperatures, the rotational modes do contribute to the energy and it'll be is 2 over 2 kBT. And for vibrational modes at low temperatures, it does not contribute, but at high temperatures, it contributes kBT. So yeah, so that's basically it for the diatomic molecule, and that fully explains why this graph is as such, because at higher temperatures you unlock rotational and vibrational modes. However, there's one interesting point to note before we conclude the video, and that is that realize that I appears in the denominator over here. So actually, right, for monoatomic molecules, previously we calculated that it's 3 over 2 because we did not account for the rotational modes. But it is actually wrong to say that monoatomic molecules do not have it's wrong to say that monoatomic molecules do not have rotational modes. Monoatomic molecules, they have a moment of inertia also, and hence they can rotate. However, because their moment of inertia is really, really small, this transition temperature is really, really high. So in order to unlock the rotational modes of monoatomic molecules, then you need to go to very high temperatures. So that is why we just take the energy of monoatomic gases to be 3 over 2 instead of 5 over 2, because to assess their rotational modes, to get 5 over 2, we need really high temperatures. So yeah, I hope that clarifies some doubts you have about heat capacity and degrees of freedom, and I hope that this video has been insightful to you, in that sense that you have learned about how we can apply statistical mechanics and how quantum mechanics is relevant to high temperature observations like these. So this graph is a result of quantum mechanics, and we see that the transitions happen at high temperatures. So it's a because usually you think that quantum mechanics is only at low temperatures, right? But no, turns out quantum mechanical phenomenon can be seen at high temperatures as well, at really high temperatures. So yep, that is it for this video. If you did enjoy this video, leave a like and subscribe, and yeah, comment also if you want to give feedback. Yeah, bye.